Hi and welcome to topic 14.2, hybridization. In this topic we're going to look at the hybridization and how we can use that to understand the different bonds and how they look like. In the hybridization we can see it is a result from the mixing of atomic orbitals, and the reason behind this mixing is that it can contain a lower mean energy level. So it's energetically favorable to proceed with this hybridization, and it can also form some bonds to other atoms in this hybridization. So we're going to look at the hybridization, and we're going to look at three different kinds of hybridization. We call it sp3, sp2 and sp hybrid, and we're going to look at specific examples of methane, ethene and ethyne, and how this hybridization can help us to understand how they can bond to different atoms. We're going to start looking at just carbon, because carbon is the central atom in these three different compounds. So if we look at carbon, and we can see in section number 6, the periodic table, here that carbon has the atomic number of 6. It means it has 6 electrons. So the electron configuration is 1s2, 2s2, 2p2. If we draw the atomic or the orbital diagram, here is the energy level like this, and we have 1s that contains 1 orbital. We have 2s that contains 1 orbital, and then we have 2p that contains 3 orbitals. Then it's 2 electrons in 1s, 2 electrons in 2s, and then we have 2 parallel spin for the electrons in 2p. So we have 1 electron like this and 1 like that. So this is the ground state for carbon. Now carbon can create 4 identical covalent bonds in, for example, the methane. But if you look here at the valence shell, we can only see 3 bonding sites. And how can they form 4 bonds when there are only 3 possible sites to connect electrons? Well, they do that by the help of hybridization. So we're going to look at this one more with a better picture. So what will happen is that when carbons will create this bonding with the hydrogen, the first thing will happen is that the electron in 2s will get excited, and it will move up to the 2p orbital like this. What will happen later is that the 2s and the 2p will merge together. So you can see that the energy level will decrease a little bit, so it will have a lower energy level than it has from the beginning. And it will create this sp3 hybridization. So the sp3 stands for orbital s and 3 orbitals in the p sublevel. Now you see you have 1, 2, 3, 4 places where we can bond into electrons from another atom. So once again, this is the ground state. What will happen when the carbon are going to bond with, for example, hydrogen in methane is that this electron will jump up to this energy level here, create this excited state. This is excited, it means it has a high energy level. And we know that nature is seeking a low energy level. So what will happen is that the 2s and 2p will merge, come together, and we have a decrease in the energy level. And from that we now also have 1, 2, 3, 4 places to bond in with the hydrogen. We call this mixing or this merging and hybridization. So carbon goes again in methane. We're going to draw it also. We have carbon here, and we have a bonding. We can see here that we have 1, 2, 3, 4 sp3. So if I'm drawing the bonds here, we have 1 sp3, 2, 3, and 4. sp3, 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 and sp3. So what will happen here is that we have 4 hydrogen atoms, and we know that they have an s orbital because it has the atomic number of 1. So we have 1 hydrogen here, 1 hydrogen here, 1 here, and 1 here. Methane has the CH4 in chemical symbols. We can see that the sp3 to the s orbital will create a sigma bond. So we have 4 sigma bonds that will be between the hybridizated sp3 and the s orbital from the hydrogen. So we have a sigma bond creating here, 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 and here. So now we understand more of how this sigma bond can be created between the carbon and the hydrogen in methane, for example. The result of the bond angle will be 109.5. So bond angle 109.5 degrees. This was when we have the possibility to connect 4 hydrogen atoms in the carbon for the methane. We're now going to look at the next kind of hybridization, and that is what we call the sp2. And in this case we're going to look at ethene, also a bond between 2 carbons, and then we have only 4 hydrogen atoms instead. Once again, this is a ground state for carbon. We have 1s2, 2s2, 2p2. What will happen is that once again this electron will go over to the excited state, and then we'll have a merge, but not the whole way through. Only 2 of the p orbitals electrons will merge to the s. So you can see that we have 1 left here. This will create this sp2 hybridization, 1 for the 2s and then 2 from the p orbitals that will merge. So we can see we have 1, 2, 3 places to bond with a sigma bond, and also here we have 1 unhybridizated p orbital. So if we take a closer look to ethene, we have 2 carbons, and the carbon has 1, 2, 3, as I said, sp2 hybridization. Like this. sp2, sp2, and sp2, and then we also have 1 unhybridizated p orbital like this. And then we take the next carbon. It also has an sp2 hybridization like this, this, and this, sp2. And then 1 unhybridizated p orbital that is left, so we can have like this. So what will happen here is that we have the possibility to create a sigma bond between the 2 carbons, between the sp2. So here we have a sigma bond. We also have hydrogen here and here and here and here. That will create a sigma bond between the hydrogen's s orbital and the sp2 like this. And then we have 2 p orbitals, and here we can see the overlap that will have the electron density over and under, so we can see that we'll create 1 pi bond. And we know that a double bond is the same as 1 sigma 1 and 1 pi bond, so we can see that it's a double bond in ethene. So ethene will look like this if I'm drawing a little more simple. Like this. So sigma bond, sigma bond, sigma bond, sigma bond, sigma and pi bond. The bond angle here will be 120 degrees. So that was the sp2 hybridization, where we can see it can occur for carbon in the ethene molecule. The next thing I'm going to show you, or the last thing, is the sp hybridization, and in this case we're going to look at ethyne. The same ground thing here, we have a carbon in ground state. This carbon will get excited, but in ethyne we can see that only one of the p orbital will merge into the 2s, and two of them will remain unhybridized. So we have an sp hybridization, 1s, 1p, and then these two remain as they have done before. So I'm not going to draw the ethyne molecule. We have one carbon who has, once again, two sp here that can form this sigma bond. So one sp hybridization here and one here. And then we have two unhybridized p orbitals. So we have 1 and 2. And then we do the same for the next carbon. We have an sp hybridization, two of them, sp and sp, and then we have two p orbitals. Of course, one will be in the y-axis and one will be in the z, but it's really hard to draw it in its 2D molecule here. And of course we have the hydrogen with the s orbital here and here. We can see that when we create a sigma bond between the two sp and between the s orbital from the hydrogen and the sp here. So sigma and sigma and sigma. And then we have actually two pi bonds between the two p orbitals here. So we have 1, 2 pi bonds. And the triple bond between the carbons in the ethyne, like this, will contain 1 sigma and 2 pi, and then we have the sigma bond between the carbon and the hydrogen also. The bond angle here will be 180 degrees. And that will give us a linear shape. The last thing I'm going to show you is a summarization here. What kind of bond we can see it will be created depending on what kind of atomic orbitals that we can see the overlap. If we have two normal s orbital together, they will create a sigma bond. And that can happen, for example, between two hydrogen atoms in the hydrogen gas. If we have one s and one p, also a sigma bond can happen, for example, in an hydrogen and chlorine atom in hydrochloric acid. And we can also have a p to p end-on. That also is a sigma bond when the two p orbitals will be like this together. Then we can see it's a sigma bond. But if we have unhybridized orbitals and s, that is a sigma bond, and also between the two hybridized. And then we also have the p to p sideways. So this table is a summarization of both 14.1 and 14.2. So this was hybridization and the structure of methane, ethene and ethyne. Thank you for watching.